Okay, so yesterday we discussed about PMOS, NMOS, IV characteristics. Okay. Then we discussed what's the need of studying analog design. Okay. So any doubt in yesterday's class? I think you might have already studied, so there may be no doubts. Okay. Anything you want to discuss regarding yesterday's class or syllabus? What about the lab? Anyone tried? Is it working? Cadence is working? That Monday batch. Anyone has tried? No response. Okay, so if you have any doubt, you can ask. Okay, we'll start the class. Okay, so yesterday we finished up to different regions of operation in mass transistor. Okay, so what is the condition for saturation? Then what is meant by edge of triode region? So edge of triode region means gate to drain voltage should be equal to threshold voltage. If gate to drain voltage less than threshold voltage, then the region is called as saturation. Fine. So mainly we need to remember this thing. Saturation means gate to drain less than VTS. If drain voltage become higher than gate voltage, then triode region will happen. Oh, I'm sorry. Sorry. If gate voltage, okay, become higher than drain voltage by threshold voltage, then triode region will happen. Okay. So it should be less than threshold voltage. Fine. Okay. So today we will discuss about MOSFET transconductance and second order effect. We already studied second order effects in device physics, no? Body effect, channel in modulation, and subthreshold conduction. Am I right?
Yes, sir.
Okay, so today we will just analog perspective, what is important. Like it only we will study. We will not study how the second order effects happening in terms of device level. We will see analog perspective, what is needed, that only we will study. Okay, so device perspective, I will recap the thing. Theory I will explain. Then how to model that theory in terms of equation for analog perspective. Right. So first, before that, we will start the transconductance. So what is meant by transconductance? Okay, let's take NMOS transistor. Okay, so input we are applying gate to source voltage. So this gate to source voltage will introduce a current. That means you can see input is converted to current. Then it current is passed to the resistance. Then current will be converted to a voltage. Fine. So what is basically a MOSFET? It converts voltage to the current. Fine. So that conversion can be defined as transconductance. Okay. So change in ID with respect to the input gate to source voltage. Okay, this thing you already derived in device physics, so you know this equation mu n C R W by L VGS minus VTS. You can see this is the same expression for R on, but the only difference is R on is it will come in denominator. This expression will come in denominator. So GM R on are inversely related. Okay, R on means in triode region resistor. Okay, so this expression you already know. So remaining two expression for GM we will derive it. So this expression is already discussed in STC. Okay, now how to get this remaining two expressions? Okay, what is ID? Let me write here. ID equal to in saturation region. Okay, half mu n C of W by L and VGS minus VTS whole square. Fine. So I want to substitute VGS minus VTS in this expression. Okay, from this I can write what is VGS minus VTS root of 2ID divided by mu n C of W by L. Am I right? Okay, then substitute here. Okay, substitute VGS minus VTH here. Okay, so you can see, let me, okay, I want some blank page. Okay, so I'll move it here. Okay, so now what is GM? GM equal to mu n Cox W by L VGS minus VTS. So what is, we know that from ID equal to half mu n Cox W by L VGS minus VTS whole square. So from this we will get VGS minus VTS equal to, so 2 ID divided by mu n Cox W by L. Okay, this is square VGS minus VTS. Now we want to find VGS minus VTS, so root. Fine. So this is equation 2, this is equation 1. So put 2 in 1. Okay, so we will get GM to mu n Cox W by L into root of 2 ID divided by mu n Cox W by L. So you can see here mu n Cox W by L, here root. So okay, so finally it will come, everything come in root. So root of 2 ID this time. This thing root getting cancelled. So root of mu n Cox W by L. So you can combine it, mu n Cox W by L. So this is one expression for GM. So already we know known expression for GM is mu n Cox. Okay, what is a known expression? Yeah, this is known expression. By substituting VGS minus VTS, we will get other expression. Okay, so now one more expression. So this expression we derive, and one more expression 2 ID divided by VGS minus VTS. Fine. So now, okay, what is ID? Of mu n Cox W by L VGS minus VTS whole square. Okay, so now, okay, let me try how to derive this thing. 2 ID divided by, okay, fine. Okay, so you know this expression, let me write here. So GM equal to mu n Cox W by L VGS minus VTS. Fine. So now you can see this expression I can write half mu n Cox W by L VGS minus VTS, okay, into VGS minus VTS. Am I right? Yes.
Yes, sir.
Okay, so from this expression I want VGS minus VTS. So what is VGS minus VTS? Anyone can answer? I want only this thing. So ID. Okay, so now, okay, so let me here is here. Okay, I am coming equation here. So I bring the 2 here. So 2 ID into mu n Cox W by L VGS minus VTS into VGS minus VTS. So what is this term? GM.
GM.
Am I correct? So simply I write GM into VGS minus VTS. So what is GM now? I can write GM equal to 2 ID divided by VGS minus VTS. Is it clear derivation? Can try on your own. Is it clear? Any doubts here?
No, sir.
No, sir.
So like that,
No, sir.
3 expressions. Okay, so one thing famous in terms of Rn, 1 by Rn, 2 ID by VGS minus VTS, mu root of 2 ID, mu n Cox W by L. Okay, now instead of remembering VGS minus VTS, simply you can take it as V over A. because VGS minus VTS is whatever. So root of mu and C arc WL V over day, 2AD by V over day. So widely comparing to root of 2AD mu and C arc WL, these two equations only we will widely use in design perspective. Right. So I did some publication in analog. Okay, these two equations only we will widely use. Fine, because in particularly in analog we will use the term GM by ID. So when you will do lab thing, we will understand. So we will widely use GM by ID. So what is GM by ID? 2 by V over day. You can see 2 ID by V over day. So GM by ID is equal to 2 by V over day. So this is a very famous expression. Okay, so GM by ID will define the operating region of the transistor. Either it is a strong inversion, weak inversion, or moderate inversion, like that. Okay, so these are the three expressions for the GM. Now, these three expressions, so we can plot the transconductance with respect to the three expressions. Okay, we will see one by one. The first expression is GM equal to mu n C of W by L VGS minus VT. I'm sorry, once again. Fine. You can see mu and C of W by and all. V and C axis is a device parameter. W by L we can size the transistor. So we can take VGS minus VTS as a variable. Then we can plot. Okay, you can say with respect to W by L. So it's a linear expression. Right? W by L it's a linear term because there is no quadratic term here. Okay, so it's proportional to W by L such that VGS minus VTS is constant. Not constant, I'm sorry. VGS minus VT. No, okay, I'm sorry. Okay, if you take mu for a fixed W by L, okay, let's take this and all constant. If you vary the VGS minus VTS, GM will vary linearly because this is a constant term K. So GM is proportional to VGS minus VTS. For a fixed W by L, so this term is constant. So linearly vary. So that's what linear behavior. So this plot will plotted using this expression. Now we'll come to second expression, GM equal to root of 2 ID mu n C of W by L. Again, here W by L is fixed. Okay, mu n C of device parameter constant. So GM is proportional to root ID. So root ID means definitely it's a parabola. Okay, it's a parabola behavior. Is it clear?
Yes, sir.
Okay, thank you. So now the next expression, GM equal to 2 ID, okay, divided by V over day. Fine. So let's assume ID is constant. Okay, that means ID is constant means it's proportional to 1 by V over day. Inversely proportional. Okay, so we can plot GM with respect to these three equations, assuming any one of the parameter is constant, vary the other parameter. So I hope you understand this thing. Okay, so now this is a large signal variation. Okay, so VGS is varying wide. Okay, in high value. Okay, large signal varying in large signal. Okay, not in small signal. I'm increasing the variation VGS minus very high. Okay, in large magnitude. Okay, so but analog we are particularly interested in bias point. Okay, so what is in the bias point or Q point? That means let's take here. Let's take some curve. Okay, I am operating the transistor in this point. Okay, in this point applying very small signal, not a large signal, very small signal. Fine. So very small signal. Okay, that means very small amplitude. Okay, I'm taking here in this region. So when you take in this region, I magnify it. Whatever this, that line is looking linear. Am I right? Slope is constant. Yes. Am I right?
Yes, sir.
Here
Yes,
slope
sir.
is exponential, but
Yes, sir.
when I operate here, it is linear behavior. So at this point, we can model our transistor in LTI model. What is LTI? Linear time invariant. That you studied in signal system, no? But so I can model actually transistor is a non-linear, because you can see the equation for ID is non-linear thing, but I want operate in a linear. Okay, so you can see I can fix the transistor at this point so that I can model the transistor as a linear behavior. So operating the transistor Q point, modeling as a linear behavior, it's called as small signal modeling, because we are applying small signal analyze the transistor, small signal modeling. That means what are the parameter you are what are the parameters you are obtained using small signal modeling? They are linear parameters. They are not non-linear parameters. Like what are the small signal parameters? Gain. Okay. Then input impedance, output impedance, everything. The parameters you are obtained using modeling the transistor in a linear region. That parameters are called as linear parameter or small signal model parameters. That non-linear behavior won't come into picture. Okay, we are interested in studying the small signal behavior. Okay, so simple example is gain. Gain is a small signal obtained from the small signal modeling. It's simply a linear parameter. That means when you apply, let's take gain of 10. When you apply input signal 1 millivolt, what will be the output?
Millivolts.
10 millivolt.
10
If
millivolt.
we apply input signal 5 millivolt, what will be the output? 50 millivolt.
50
Am I
millivolt.
right? So what you do here? V out. Let's take here V out. Here V in. So what are you modeling? V out equal to A gain A V into V in. So it is a linear equation. Am I right? But practically, okay, due to the distortion inside a transistor, okay, there will be a higher order JV equal to V in. Okay, some non-linearity in terms of V in square. Okay, some non-linearity term will be there. But what you are doing, we are operating in a small signal point, so that non-linearity term is are negligible. They assume like that. But practically, non-linear terms will be there. Right? So that's the thing. So now we want to model transconducting as a small signal parameter. Right? So for that, okay, so you know GM equals to what is GM? Mu n C of W by L VGS minus VTH. Fine. For fixed VGS minus VTH, GM will be constant. Okay, that means we are operating transistor in saturation region. So okay, so saturation region. Okay, we will fix the VGS minus VTH. Fine. So then vary VDS. Okay, so here we didn't consider channel modulation. Okay, so according to the square law equation, GM will be constant. If VGS minus VTH is constant, that means fixed, GM will be always constant. You can see GM is always constant above the in saturation region. But in triode region definitely GM will decrease, because triode region you are GM is with respect to the VGS minus VTH. Okay, because Rn no. So what is Rn? Okay, GM equals, so first we write, so mu n C of W by L VGS minus VTS. But so when you go to the triode region, if you decrease the VDS, okay, so GM will decrease, because we cannot use the same, you will use this equation. Okay, so for GM, what you derive? We derive this GM in saturation region. Okay, so let me write here. Okay, so what you derive GM in saturation? Dou ID by dou VGS. So what is the current equation here? What is the current equation in saturation?
Mu1
Of
of
mu
W
n
by
C of W by L
VGS minus VT
minus
whole
VTH
square.
let Just 1 minute, I will turn on my laptop charger. Now, I want to derive GM for triode. Same expression dou ID by dou VGS. So what is the current equation you need to consider here? General equation mu n C of W by L VGS minus VTS into VDS minus VDS. So any doubts here?
No, sir.
Yes. So now we can see when I do dou ID by dou VGS, I can say definitely proportional to VDS. Am I right? So when VDS decreases in triode region, GM is decreases. In saturation region, GM is always constant. In triode region, GM is decreasing. Right? So that's a behavior. Okay, so I hope you understand the transconductance. Okay, similarly for PMOS, okay, in terms of VGS, we need to put VHG or mod VGS, or simply put a negative sign there. So okay, instead of remembering negative sign, okay, so you can think like GM equal to mu P C ox W by L VHG minus mod VTX. Okay, similarly 2ID divided by VHG minus mod VTX. Okay, similarly root of 2ID mu P C ox W by L. These are the GM equation for PMOS. Okay, so that's all about transconductance. Now we'll come to second order effects. Okay, first we'll start from body effect. Can you remember what is in the body effect or backgate effect?
Body and source are shorted.
Okay, what is the effect of body effect? No, source and bulk are shorted. That's fine. I understood. Okay, so what is in the body effect?
Threshold voltage is controlled by body terminal.
No. I'm asking. That is okay. So let me write. Okay, I will write here body effect. Fine. Now, please listen to what I am doing. Let's take two transistors are there. Okay, M1. Okay, M1, M2. Fine. So you know, in a P substrate. Okay, so let's take NMOS. N plus, N plus. So this is source. This is drain. Okay, I can put the gate. This is gate. This is oxide layer. This is P-type semiconductor. Now, you know, NMOS P substrate always to connected to VDD or ground?
Ground.
Ground. Fine. So you can see always you will start source and bulk. That means source you are connected ground. Okay, you can see let's take M1 transistor. Okay, this is M1 transistor. Okay, source is connected to ground. So source is connected to ground. That means source and bulk are shorted. Okay, I can think like this. Am I right? Okay, now we'll come to M2. For understanding purpose, I didn't put a gate. Don't mistake me. Okay, P substrate connected to ground. What about source terminal in M2? Is it connected to ground? Let's take this node is drain. Okay, so this is a drain of M1 transistor. Where it is connected? Is it ground?
No, sir.
No. Where it is connected? It is connected to drain of, okay, It is connected to drain voltage of M1 transistor. Okay, so now you can see whether here source to bulk voltage is 0. What about here source to bulk voltage? Is it equal to the drain voltage? Drain voltage of M1?
Yes, sir.
Am I right?
Yes, sir.
So definitely there will be a source to bulk voltage in cascode transistor. Okay, if source to bulk voltage there, what about threshold voltage? It is same or it will vary?
It will vary.
It will vary. That effect is called as body effect. Why it's coming? Because that is due to body. Am I understandable? Is it understandable what I'm saying? So you can see if you are increasing the body voltage, okay, source to bulk voltage is okay. So now you can see source is n plus here. So VS, let's take VSB. It's greater than 0, less than 0. Is it greater than 0, less than 0? You can see here P is ground, source is positive voltage. So source to bulk, is it positive or negative value? Are you listening?
Positive.
Positive, greater than 0. Okay, let's take source is N. I'm modeling this PN junction. Okay, so this is a source terminal, that is N plus, then P substrate. P substrate connected to ground. Okay, here some voltage there. Right, so here higher voltage. So this is forward bias or reverse bias?
Reverse.
Reverse bias, good. So reverse bias means depletion region widens or decreasing. If you
Depletion
increase the
widen.
VSB,
Widens.
widen. So depletion region widen. So depletion region widen means which charge will increase? Mobile charge or immobile charge?
Immobile
Immobile
charge.
charge.
Immobile charge.
Good.
Immobile charge.
Immobile. That means what is immobile? That ion, that the intrinsic, that charge available at neutron, not in the outside cell. Okay. So immobile charge. So you understand this thing? Any doubts here? Okay. And now this is without the body voltage. Now we can see when you increase the body voltage, VSB greater than 0, so immobile charge is increasing. Is it understand? Depletion is in widening. Am I correct? Yes?
Yes, sir.
Yes, sir.
Increasing QD. Now, before going to why the threshold voltage increasing. Now, let's take MOS transistor. I am coming to device level. P substrate. Okay, so how the MOS transistor behavior when VGS greater than VTS? How the inversion layer formed? Okay, let's take P substrate. Okay, here N plus. So in P substrate, what are the majority carriers?
Holes.
Holes. Okay, so many holes are there. Okay, I simply put hole because it. Okay, I will put hole like that. Okay, so now, okay, how the inversion layer forming? Where the inversion layer? What is in the inversion layer? What is in the inversion layer?
Channel will form between source and drain.
Channel.
Will form between source and drain.
Okay, this is the inversion layer. So, okay, so you are good. Okay, this is a inversion layer. Why it is called inversion layer?
It is of opposite charge to the substrate.
Huh? Okay, inversion layer. What are the carriers in the inversion layer? In NMOS?
Charge is balanced.
What are the carriers? Hole or electron?
Electrons.
Electrons.
Okay, so electrons are there. Okay, in the inversion layer, whether hole concentration higher or electron concentration higher?
Electron.
That's what you know, because this is also inversion layer also belong to the subset, but in this region, it behaves as a N-type semiconductor. That means in this region only, N type, that means electron concentration. Okay, let's take ND. Okay, electrons concentration higher than hole concentration. So that's what this layer only called as holes. Sorry, this layer only called as inversion layer. That's what the name inversion means. The behavior of P will become N. Am I right? What I'm saying is understandable? Yes.
Yes,
So,
sir.
Yes,
and
sir.
now let's take VSB equal to 0. There is no body effect. Okay, this is a depletion agent. Fine. So, okay, there will be what is charge neutrality? What is charge neutrality? Number of mobile ions equal to number of immobile ions. Am I right?
Yes, sir.
Okay, so what here holes are measured. What is immobile ions? What are immobile ions here?
Na,
E type.
Na,
Yes.
acceptor ion.
Okay. Now let's take the same thing. I am increasing. Okay, let's put a red color. I am increasing VSB greater than 0. Okay, VSB greater than 0. So more immobile ions are coming. So what will happen? We need to more immobile ions are there. Fine. So accordingly, more holes will be created. Am I right?
Yes, sir.
Yes. Okay. That means we need to overcome. We need to apply some more voltage to turn on the transistor. That means inversion layer should happen. What is the turn on transistor? Inversion layer should be formed. Is it understandable? Okay. Previously, some holes are there. So due to applying more VSB, more holes are created. Okay. So we need to apply some more voltage because additional voltage we need to apply. So let's take del V. Then only inversion layer will form. Is it understandable what I am saying?
Yes, sir.
So what is the voltage to turn on apply? What is the voltage term we need to apply to turn on the transistor? That voltage is called as
Threshold voltage.
threshold voltage. Good. So due to body effect, depletion charge increasing. Okay, so we need to apply some more voltage to turn on the transistor. So threshold voltage is increasing. I hope you understand the way I explained. Okay, so increasing QD, so VSB increases. It widens the depletion agent. That means immobile charge increasing. So that will increase the VT. That's a body effect. Okay, what is body effect? Is you vary the body voltage. What effect? That is called body effect. Okay, so it is also called as backgate because we are not varying. So previously we are varying the gate voltage. Right? Previously we are varying the gate voltage. So VGS greater than VTS. We will make a transistor on. But now vary the body voltage. Vary the body, it will increase the threshold. Okay, so it is also having some effect in the turning the transistor on. So that's what it is called as backgate. Body is called as backgate. Okay, so this effect is called as backgate effect. So body effect or backgate effect. Okay, so what I want to convey is comparing to M1. So what is VTH of? Okay, let me write in blue color. So VTH of okay, it's not coming. Don't mistake me. So VTH of M2. So which threshold voltage is higher? M2 or M1?
M2.
M2. Good. This understanding is needed. Due to body effect, threshold voltage of M2 is higher than M1. Even though both are NMOS same transistor, due to body effect, okay, M2, the threshold voltage of M2 is higher. So this is called as body effect. You understand very simple manner. Okay. Fine. Okay, so you can see we can model. We told me threshold voltage increasing. That can be modeled with this equation. Okay, so this is ideal threshold voltage. Okay, due to source to bulk. Okay, source to bulk. You know, just now I explained. Okay, I'm sorry. You can see source to bulk. So VSB. So this is VSB. And so VSB, that means reverse bias for bias voltage. Reverse bias voltage increases, depletion agent increases, but it will increase the threshold voltage. So VSB increases, threshold voltage increasing. So VTH is proportional to, so you take root VSB. Fine. So now this behavior you understand. Okay, so now I am putting this instead of forward bias, okay, sorry, reverse bias. If I put forward bias, what would threshold voltage? So forward bias means VSB less than 0. VSB less than 0, threshold voltage increase or decrease?
Decrease.
Okay, so let me explain. I will come in this perspective. Okay, so VSB less than, it will become forward bias. Okay, so less depletion charges. That means you can comparing to ideal less depletion charges. That means you can easily with less voltage you can make the transistor on with less voltage. That means threshold voltage decreasing. That means VSB is negative. So VSB is negative, threshold voltage will decrease. Is it clear? That's what we need to be careful. VSB should be always greater than 0. If it is less than 0, threshold voltage decrease and this junction will become forward bias. Okay, instead of current flowing here, it will also flow here because PN junction. No? Is it clear what I'm saying? What is your objective? Current should flow from source to drain. It should not flow here. So always would avoid. Okay, so source to bulk should be always in a reverse bias. If it is forward bias, there will be some current leakage. Is it clear what I'm saying?
Yes, sir.
Good. Okay, so now we can see this is ideal transistor. Now we'll vary the body voltage. Okay, so what is a without body thing? So what is VGS here? VGS is 1.2 volt. What is ideal threshold voltage? 0.3 volt. So VGS minus VTH, how much this thing? 1.2 minus 0.3, it is 0.9. So it is definitely greater than 0. So ideally transistor on. Okay, gate voltage make transistor on. This is due to gate voltage. Now we vary the body voltage. Okay, you can see when you keep on increasing the VSP. Okay, keep on increasing. That means you can see Vx minus Vs. Okay, so this is Vx, so this is VSP. Oh, I'm sorry. Okay. Okay, so what do you want? VSB. Okay, here Vs is 0, so 0 minus Vx. So VSB is minus Vx. Okay, so I want to increase VSB. That means I want to decrease Vx. You understand? And what I want to convey? It's a opposite thing. So Vx should be decreased. That's what negative Vx. What are opposite thing? Fine. So if I increase VSB or decreasing Vx. Okay, so decreasing Vx, VSB increasing, threshold voltage is increasing. Am I right? Is it understandable what I'm saying?
Yes, sir.
Okay, so decreasing Vx means, okay, decreasing Vx means, okay, increasing VSP. That means threshold voltage is increasing. Okay, so at particular point, it will make transistor off. So what is the particular point? So when the transistor will be off, VGS is equal to, that means less than or equal to VTS. Okay, so due to VSB is increasing, so threshold voltage increasing. Okay, so when what is the VGS value you assume? 1.2. Okay, so when VTH becomes 1.2 volt, so what is VGS minus VTH? Anyone can answer? Okay, you know VSB increases, threshold voltage increases. Okay, when threshold voltage become 1.2, that means it is 1. What is 1.2? This is a VGS value. So it is equal to VGS value. Okay, when threshold voltage equal to the VGS or 1.2 volt, what is VGS minus VTH?
0.
0.
0 volt. So what is VGS minus VTH? 0 volt means transistor is on or off?
Off.
Off. That means till now what you studied, using the gate voltage generally we will make the transistor on. But now using the body voltage also we can control the transistor behavior on or off. So that's what it is called as back gate behavior. So that's what body is also called as back gate. It is also having gate effect. What is the purpose of gate? To make the transistor on off. That's what you study in digital. Okay, so by applying the gate OLL, you make the transistor on or off. Similarly, using body terminal also, we can make the transistor on off. That's what it is called as back gate. Gate terminal, body terminal, it is also called as back gate. So the effect is called as back gate effect. I hope you understand this thing. Okay, so fine. Now you can see this is a source follower. We will study in amplifier, but you can see here also body effect is there. Yes or no? You can see source is here, body is here. So definitely threshold voltage not a ideal thing. So there is some VSB voltage. So I can write a equation. So you know current equation VGS minus. So this is gate, source, drain. Okay, so VG is V in. What is VS is V out. Okay, so VGS minus VTS. Okay, so ideally, if threshold voltage is constant, right? So to make the current constant, V in minus Vd is always same because current is constant because you apply current source here. So if you increase V in by small amount, it will vary by small amount to make current is constant. That's what V in minus V out is. The difference is always constant to make the current constant or to make ID constant. Okay, so this is we assume threshold voltage is constant. Now we assume threshold voltage due to VSB. So what is VSB in this? Anyone can say what is VSB here?
V out.
V out. So now you can see V in minus 2 V out. Fine. So now it is not a, so there will be some non-linear behavior. The difference to make current constant. Okay, to make current constant. So V out should vary differently to make current constant. So this is a non-linear behavior. So what is thing? What is a linear? Small segment. So whatever input you are applying, same variation should be in wave. That means the difference should be constant. But now you can say this is a non-linear behavior. Why is non-linear behavior happening? Due to body effect. Okay, so what do you understand? Body effect will introduce a non-linear behavior in the transistor characteristics. Okay. Okay, so we'll discuss about channel and modulation and subthreshold leakage. Okay, so after that we'll finish it. Okay, so now channel and modulation. So what is channel and modulation? Anyone can remember? What is in the channel and modulation?
Current ID becomes proportional to VDS.
That's fine. Okay.
When VDS is greater than VGS minus VTS, then channel length modulation.
What it will do? How will affect the behavior in the IV characteristics? You can look on the figure here. By looking on the figure also you can say. You can look on the figure I can say.
In saturation region there will be slope.
Slope is non-zero.
Okay. That means let's take for a given VGS without ideal equation. What are this thing? Constant, am I right? Am I right? Always constant. Ideal current source. If channel in modulation one plus lambda VDS. Now we can see whether current is constant. Whether we can say current is constant here? Yes or no?
No, sir.
No. Why? Because due to channel and modulation effect, current is not constant. Okay, so what is a MOSFET? We can see MOSFET. We can say voltage control current source because ID is converted to the sorry, when you apply input voltage, convert to a current source, constant current. But due to channel modulation, it will affect a constant current behavior. Right? That's what the term is 1 plus lambda VDS. Okay. So now, how to model this channel and modulation behavior studied already. Okay, so simply multiply by 1 plus lambda VDS. So what is lambda? Channel and modulation parameter? It is proportional to 1 by L. Okay, when you increase the length, we can reduce the channel and modulation effect. So we can see here, when you increase the length, we can reduce the effect. That means we can reduce the slope. Right? So we can minimize the channel and modulation effect. Fine. So then with the channel and modulation, okay, so we can derive the GM also. So 1 plus lambda VDS additional term will come. Okay, but practically we'll assume this term is very, very small. So practically use only this expression. So don't worry about the GM with respect to lambda VDS. Okay, so if you assume that things will become complicated, we cannot analyze by paper. Okay, so practically for a design perspective, for GM, okay, we'll neglect the channel and modulation effect or lambda effect. So, okay, so now when you increase the length, so just I mentioned lambda proportional to 1 by L. When you increase the length, okay, the effect reduced by order of 4 divided by 5. Why? Because ID proportional to W by L into lambda VDS, 1 plus lambda VDS. Okay, so lambda means 1 by L, already 1 L is there, so 1 by L square. So if you increase the length, okay, so it will the effect reduced by quadratically. Is it clear? Okay, so the final thing is subthreshold you have studied, no? Yes? Am I audible?
Yes,
Hello? Not respond.
sir.
Yes, sir.
Okay, so subthreshold thing, okay, I will finish within 5 minutes. Okay, so VGS lesser than greater than VDS square law. Okay, so VGS greater than VDS. But when VGS less than VDS, we assume there will be no current, but practically there will be some current is there. That current will behave like a exponential. Exponential means BJT. Okay, so you know PN junction diode equation. Similar thing PN junction equation, but VGS divided by eta, that subthreshold swing factor, zeta. Okay, so what this subthreshold behavior is explaining, it's exponential. Okay, when the decade in, okay, this is exponential in terms of log curve. Okay, the current will decade by decrease by decade by applying the gate voltage of 80 millivolt. That means if you apply gate voltage 10 millivolt, that means del VGS you are decreasing by 10 millivolt. Current is reduced by the factor of 10 decade. Decade means 10. Okay, so whenever you are applying the 10 millivolt, when you are applying 80 millivolt, current is reduced by 10. So that means if you apply 160 millivolt, what will be the reduction? Decade and one more decade. So how much it will come? 100. Am I right? Respond. Okay.
Yes, sir.
Okay. So now you can see this I naught. So what is this I naught? I naught equal to 2 zeta beta. Okay. So I don't want to write the beta. Let's take n mass. Okay. So mu n C of W by L Vt square. Vt is thermal voltage. So you can see I naught is proportional, remaining and all constant. So I naught is proportional to W by L. So zeta is 1.5. Here zeta mentioned as 1. So it is approximately 1.5. So Vt is a thermal voltage. So now you can see I naught is W by L. Okay. So now this is a plot of this subthreshold current. Fine. So you know we are having two equations, ID in saturation and ID in subthreshold of BT. Fine. So now this sub-VTH is also called as weak inversion. Why is called weak inversion? The voltage about threshold voltage. Okay, if you apply more and more gate voltage, that is called as strong inversion. What is by strong inversion? You studied strong inversion, weak inversion. That means what is the inversion refers here?
Inversion charge.
Inversion layer. Okay, inversion charge. Okay, what you assume in VGS less than VGS, we thought there won't be any conduction. That means there won't be any inversion layer. But there will be some inversion layer, but that is weak. Very small current is there. So that's what this region is called as inversion, weak inversion. VGS less than VTX called as weak inversion. The current expression VGS weak inversion is exponential behavior. Okay, so one thing you want to remember that zeta should be 1.5. So current will decrease by decade for a VGS when you apply less when you vary VGS by 80 millivolt. You need to remember this thing. That's all. Remaining and all not that much important. Okay, so the breakdown you already studied. So when you apply more drain source voltage, the junction will break down. Okay, we need to take care of the device. Okay, that's all. This is called punch-through effect. So this is not that much important. So that's all about the second order effects. Okay, we studied about body effect. So body effect when source to bulk voltage is higher, threshold voltage is increasing. So that will introduce a non-linear behavior. Then we discuss about the channel length modulation. So due to channel length modulation, the current is not constant in the saturation region. So when you increase the channel length, that lambda is proportional to 1 by L. No? So when you increase the channel length modulation can be reduced. And then we discuss about subthreshold conduction. So avoid the subthreshold. Below the threshold voltage, there will be some conduction there. The conduction behavior can be explained using the BJT exponential behavior. Okay, it is also called as weak inversion. There is some small inversion layer is there. Okay, so that's all about today. So then we discuss about transconduction, different expression for transconduction. So any doubt? Let me take the attendance.